Okay. Hello everyone. Good afternoon. Almost going to be 12. So basically today I will be delivering a session on OpenFOAM, and in this first session I will basically introduce you to OpenFOAM and its tutorials, case structure, and depending on the time permits, we will go a bit towards a bit of programming. I will show you where the source codes are located, where you can see actually the codes written. How can you take that code and modify yourself, and how can you make your own solver? So it's a bit, if you really want to learn it step by step, it's a subject matter of 1 week at least. So I have to tell it in 1 hour, which is almost impossible. So, but I'll try to go very slowly. So keep asking me questions, but the idea is to give you again an overview. And I see only 4 or 5 laptops. So how many of you have laptops with you with OpenFOAM installed? Here. 1, 2, 3, 4, 5, 6. All right, 6 out of around 30. So, I mean, just rest of the participants be assured that it will be a demonstration. So I don't expect that in 1 hour you will be able to do everything with me because of the lack of time. But since the session is getting recorded, so you can go back and try it with your own laptop and open, and you can ask me if you have any questions. All right. So with that expectations, is that clear? The outline of the first session would be from very basics, like to introduce you what is OpenFOAM, how the case structure of the tutorials look like, where the source codes are located, what are the solvers that you might want to actually use for fluid structure interaction, what a basic code or a solver in OpenFOAM looks like, how you can modify it and compile it as your own solver. So that I will try to cover all of these very briefly and give you an overview. And continuing with that, in the afternoon session, I will go towards the fluid structure interaction problem. And I will show you, as I promised in my first session, I will talk about 2 different methodologies. One is mesh morphing, another is basically overset meshing strategy. So how these 2 different dynamic meshing strategies can be implemented to solve first rigid bodies which are moving with prescribed motion, and then how we can couple it with the fluid, of course with the limited degrees of freedom, because we won't have time to go towards a continuously flexible object. Okay. So any queries on that, on the expectations of these 2 sessions? If not, yes, please.
About the fluid structure interaction problem.
Yes.
So from that, we need to install another one related to the
No. I will demonstrate you like the problem of vortex-induced vibration, which Professor Mittal taught you theoretically. So it will have limited degrees of freedom with springs. So our structural equation will be just a it's an oscillator equation, and OpenFOAM has a 6 degree of freedom solver which already has the oscillator equation, and we will use that, okay, for today's session. Is that clear? Okay, so how you have used OpenFOAM quickly? Can you please keep breaks just for me to get an idea. 1, 2, 4, 5. Okay. Can you their Zoom? Otherwise, it will go and I can't. Please mute your Zoom session. Otherwise, it will. All right. Now I think it's not clear. So since only 5 out of 30 people have used OpenFOAM and rest you have not used, so I will take it very slow and start with very basic. And how many of you have in general used CFD softwares like the like ANSYS Fluent or Star CCM? Everybody. So everybody knows what is CFD, what are the different principles, what are the governing equations, how we discretize them and how we solve them. But of course, I will give you the exposure to this open source library, which is called Open. All right. So now let us start with this acronym. Do any of you know what is the full form of OpenFOAM? Why is it called OpenFOAM?
Open source and field operation and manipulation.
Right. So basically, so that's the first thing I always ask everybody. When you write OpenFOAM, the FOAM is an acronym which means field operation and manipulation. So don't write it in small letters. Okay. So it's an acronym. And open is basically it's open source, available to the community, and the development is community driven. That's why it is called OpenFOAM. Okay. Fine. Let's go ahead. So those who are basically with laptop, you can note down this link. I will probably share this slide so you can have it anyways. So this is one of the wiki page of the OpenFOAM OpenCFD version, where they have systematically different repositories of tutorials which can get you started. So I will just try to show you this quickly. But before going to there, so you can see that these repositories are from openfoam.com. So I will come in a few minutes that what are the different forms of OpenFOAM that exist, because that normally confuses the beginners. And so today's session and whatever I will be showing will be based on the form of OpenCFD version, which is openfoam.com. All right. So that is one thing to clarify at the start. And I will come to this link a bit later. All right. So I have told you this, what is OpenFOAM. Now, what do you expect from these open source libraries and what you can expect to do, right? So it is a set of open source libraries for continuum mechanics. Okay. So continuum mechanics is composed of solid mechanics, fluid mechanics, both. They both are different continuums, and of course they are coupling, which is fluid structure interaction. Apart from that, OpenFOAM can deal with different multiphysics problems, such as, for example, you want to do magnetohydrodynamics, you want to do chemical analysis, coupling between chemical equations and phase change, etc. You can do electromagnetism, for example, and you can do many things which comes under the broad umbrella of multiphysics simulation. Now, for this particular session and from my expertise, we are restricted to the fluid dynamics or structural mechanics or the coupling of both, which is fluid structure interaction. All right. And the codes of these open source libraries are written in C++, which is, you all probably know that it's a language of object-oriented programming. So all the programs within OpenFOAM is written in a similar fashion how you write an object-oriented program. Like you have a namespace, you have objects within, you have classes within that namespace defined, and within the classes you have objects and functions defined. And the way you declare and call those objects and functions, you have to call them in a similar fashion in OpenFOAM. All right, but the only difference is that within the OpenFOAM programming environment, the namespace is FOAM. So that we will come to that when I will show you a source code. All right, and the CFD methodology. So what Professor Mittal was presenting and the solver, the in-house solver that he used was based on which methodology? Finite element method, right? However, in OpenFOAM, the CFD principles or the algorithms, they are written in finite volume method. That means you discretize your governing equations in finite volume methodologies. All right. So what is the other methodology apart from it in CFD that you all learn in your CFD course, which is finite difference method, right? Okay, so going ahead, why OpenFOAM? Why we want to use OpenFOAM, which I have already actually told you that it is open source. So it has a large community base, and there are community driven developments going on every day, and it is free. Of course, you don't need a huge amount of money to buy the licenses of commercial software. And I will come to this term, which is called high level programming. So for example, if you write a code to solve a differential equation in C, or for example, in C++, what do you have to do? Have you ever written any small codes in C or C++? Yes, no, maybe. So you know that you have to write each and every function yourself, right? And then you have to call those functions to use them in your main program. Now, in contrast to that, if you have used Python or MATLAB, what is the main difference? Exactly. So there are inbuilt functions which you can call through by calling their libraries or header files at the start and then keep using them. You don't have to define, for example, what is a sine function. You just write sine of x, but you don't write in a separate function what sine does. All right. So even in OpenFOAM, there are in the installation directory, there are all these functions are predefined. So you don't have to write each and every function. For example, you want to calculate the Laplacian. Now you don't have to write the code to solve for what does the Laplacian operator do. So it already is defined. We will just use the function Laplacian, and this is what is called high-level program. Right? Now, it can be, of course, as I'm telling from the day one, that it can be tailored to your specific needs, and you can modify the code. You can write your own solver. So that is the best advantage of using open source tools, and it has extensive multi-physics capabilities. It has cross-platform coupling like FSI, which means that you can couple OpenFOAM with another third-party solver. Like, for example, I showed you yesterday, you can couple it with calculates or anything else. Okay, so it has cross-platform coupling. Right. So what we can't expect. So this I saw everywhere where I've given these slides, and probably these slides are already there in the YouTube recorded somewhere. That it is no black magic. You can't click buttons and do your simulations. There is no single executables because it's a repository of libraries. So you have to know where the files are located, which function you need to use, and where it is located. Still, there is no native GUI, but there are lots going on where different developers are actually developing GUI for specific problems. And this sentence, I should actually scratch it now, that not so well documented, because these slides, when I made, it was a few years ago. But now if you actually search on online, you get hundreds of different presentations, documentations, tutorials. So it is not the same scenario what was there when I started in 2014. So basically 10 years back, there was almost no document. But now I will give you some resources where you can find a lot of documentation. So this is basically a brief outline. I mean, just for your knowing the history of it. And this particular OpenFOAM code, the basic one, the main OpenFOAM code was mainly contributed through their PhD thesis, Professor Henry Weller and Professor Howard Jason. So basically, they basically wrote the main body of the code in during the PhDs in Imperial College London. Then there was different ups and downs, whether it should be commercialized or not, and so on and so forth. But however, till now, there are 3 forks at least. Most of these materials are still open source and available to the users. Right. So this is a bit backdated, but I will tell you that what I was telling, it's very important to know which version of OpenFOAM you are using, right? Because it's very confusing. I get like at least 2-3 emails a week asking that which version should I use, or I'm using this version, whether it will work, etc. etc. So OpenFOAM has 3 versions. One is or 3 forks. Do you know what is a fork? So if you know the version control mechanisms through Git, you know that in Git, in GitHub or GitLab, whatever version you use, we can upload our code and can keep developing it, and we will have the different versions located. So like that, OpenFOAM, the main repository, are developed in 3 different forks. One is called, one is actually hosted by the OpenFOAM Foundation, which is .org. The other one, which I will be showing today, is hosted by ESI OpenCFD, and it is hosted in openfoam.com. And the third one is again mostly community-driven development, which is hosted by as Foam Extend. Now, why do we need different versions? Because these 3 different forks are developed separately. So some of the developments which have been done within one of these forks may not be available to the other. And also there may be slight change of syntax from one version to another. So that you need to know. Or you have to keep using one version, like I now keep using mostly the openfoam.com fork, so that I am very much acquainted with the changes and how it is getting developed. Okay. So now the backdated thing, which is so the recent version of openfoam.org is correct. So it's version 11. And what does this 11 means? Because every year they release a new version and they just add number 1 with it. So the current version is version 11. Whereas the openfoam.com, they release the version every 6 months. Okay. And this version 2306 is backdated. Why? Because this version was released in 2023 and 6 months, which is June. So the latest is till date is 2312. That means which is released in 2023 and December month. But in a couple of days or few days, it will become 2406, because this June they will release another new version. Is that clear? So I forgot to change that number. And Foam Extend 5 is the updated version. The latest version is Foam Extend 5. Now, just wanted to mention here that what additional things you can get from Foam Extend. If you want to use immerse boundary method or some extended capabilities of overset method or fluid structure interaction, they were actually only available in Foam Extend, but now they have been ported to openfoam.com also. Okay, so these are the things that you need to know with that. So this is very important, that when you go to any tutorial to get started with OpenFOAM, you will have a case folder, right? You will have a tutorial folder. So whenever you just click the folder, you will see a bunch of files. And then the new starters, they get confused that what are these files, which file do I change, and what do they mean, etc. So this is basic structure of any OpenFOAM tutorial, and they do not change. Now, if you add complexities to it, you have to add new direct dictionary files. However, so I will just first start with explaining the structure. All right, and then I will show you one tutorial later. So the main primary folders are 0, system, and constant. Now, people who have already used OpenFOAM, can any one of you told that what does this 0 folder mean and why it is named as 0?
Initialization.
Yes, correct. So this 0 folder, we will actually keep the boundary condition and the initial conditions at t equal to t. Okay, and that's why this folder is called 0. And within the 0 folder, you would see that you have different files named with the state variables or the field variables of your problem. So, for example, if you want to solve an incompressible Navier-Stokes equation, What are the independent state variables of the problem? Yeah, let's ask from back. Can anybody tell from the back? To solve, if you want to solve an incompressible Navier-Stokes equation, what are the state variables or the field variables of the problem? Louder, please. Okay, correct. So basically pressure, which is a scalar variable, and velocity, which is a vector. All right. And there can be another dependent variable, which can be temperature. For example, if your scalar transport equation involved heat transfer also, so you can have temperature. Now, how many independent variable will you have? XYZ is the same, it's a vector, position vector. And time, right? And why do you okay, that's fine. But then why do you both need initial and boundary conditions to solve these governing equations? For example, you have a spring and mass system, right? So the governing equation of a spring mass damper system, is it an ordinary differential equation or a partial differential equation? Ordinary differential equation. Now, what's the difference between an ordinary differential equation and a partial differential? Exactly. So basically, partial differential equation will have more than two or more than one independent variable. And to solve incompressible flow problems, we solve incompressible Navier-Stokes equation, which is a partial differential equation, and we have time as well as position vector as the independent variables, and for that reason, we need initial condition as well as boundary condition. Is that clear? So as you said correctly, if you go to the zero folder for any basic incompressible flow problem, you will see two files. One is pressure, another is velocity. And if you open those pressure and velocity files, I'll show you, it will have the boundary names that you have created in your machine, and then the corresponding boundary condition. And also at t equal to 0, how do you want to initialize the problem? Here. Now the next folder comes as constant, right? So again, why we call this folder as constant quickly? Whoever have used OpenFOAM, why do you think that folder is called constant?
The information of national property. Properties are basically.
Yeah, but why is the name valid? Why is the name constant? So these constant folders will have the first information which is related to the mesh, and though that mesh information will be located in the folder called polymesh. And we will have another file. We can have multiple files, but the another mandatory file is transport properties, which involves the transport properties is very intuitive or self-explanatory, that what is your kinematic viscosity of the problem, right? What is your density of the flow, etc., etc. There can be another file called G, which gives you the gravitational acceleration. So all these values, they remain unchanged throughout the simulation. That's the concept. So if you have any parameters or any variable or properties that will remain unchanged throughout the simulation, we keep it within constant folder. Okay. Now I will come to the second session, that if you want to move your body, like for example for fluid structure interaction problem, you need a dynamic mesh motion strategy. And for that, there will be another file within this constant folder, which will be called dynamic mesh dict. Okay, so it will be a dictionary file which will define or which will declare what type of dynamic mesh motion you want to use. Right. So the last folder, which is very important, is, so you can see that what I told this is given here. So the last folder, the primary folder is system. Now within the system folder, what are the things that you think will be located? Block mesh, yes. What do the block mesh do? So just to tell everybody who doesn't know that OpenFOAM has its one of its own meshing utility. It's called block mesh, by which we can easily create structured meshes. And so the dictionary file for creating the mesh, if we use OpenFOAM to create our mesh, is called block mesh dict, and that will be located within the system folder. Correct. Then yes. So since you want to solve the CFD problem, you have to define what are the CFD schemes, such as what are the discretization scheme, interpolation schemes for, let's say, temporal derivative, whether you want to use a forward or backward or central reference, or I'm just giving example like how you have studied in CFD courses, right? So you need some discretization schemes. How do you want to discretize Laplacian term? How do you want to discretize the divergence term, etc., etc.? And all those schemes that you will define, they will have a certain level of accuracy, whether they are first order accurate in space and time, whether they are second order accurate in space and time. So accordingly, you have to choose the schemes which will be located in finite volume schemes. Now, the next comes is the solution algorithm. Do you want to solve the problem by using Piso algorithm or simple algorithm or Pimple algorithm? And what will be your tolerances? How many correction loops you want to use? Whether you want to use, under relaxation to accelerate the convergence of the solution. All those things will be located in the file finite volume solution. Okay, so I'll show you all those files, but just giving you the idea here. And then the main thing I want the answers from whoever has not used OpenFOAM, that if you want to do a CFD simulation, what else do you need to tell the solver? To run the simulation, what are the control parameters that you need? To run any CFD simulation in any tools, what are the control parameters you need to tell the solver? Sorry?
Static or dynamic convergence criteria.
Steady transfer.
Okay, so the state coming one by one, steady or transient, that will depend on, that's true, that will depend on your solver, right? So which solver you are choosing, that is one thing. But more basic things, right? For example, when do you want to start the simulation? When do you want to end the simulation? What will be your delta T of the simulation, right? So you have to tell those information. What will be your time step in this when the simulation is running? Do you want to keep a fixed time step, or you want to use an adaptive time step based on the stability criteria such as CFL number, right? What else? How do you want to write your data? What will be the significant digits of the results that you want to write? Okay, all those things, all those control parameters, and another most important for OpenFOAM is the function objects. Which means that if you want to use any function, inbuilt function to post-process your solution, such as if you want to calculate forces or force coefficient, if you want to calculate anything else, average pressure or any average quantities, if you want to calculate wall shear stress, for example, on the go while your simulation is running, you have to use function objects, and all those function objects also has to be defined. So all these things are actually defined in a file called control dict, which is the most important file which defines the control parameters of the simulation. All right. And another important file that is located in system is called decompose file, which is used if you want to run the simulation in parallel. If you want to use multiple processors to run your simulation faster, you have to define the domain decomposition technique by which you want to divide your whole domain into different processors and then run the solutions differently. And then when the solution is completed in different processors, you have to reconstruct the solution into one. And that file is called decompose file. I think this is now clear, right? So if I give you any tutorial case folder, you now know what are the files there and what does the mean. That's the starting point. Do you have any queries in that? Yes.
And then if you want to run it in parallel, like are the code in directly parallel or you have to?
No, yes. I mean the yes, it's a good question. So the code in OpenFOAM library is written inherently in a parallel way. So you just have to use an appropriate domain decomposition technique. Okay. And then you have to solve the solution parallelly, and then you have to, and solving parallelly, you have to use the MPI library. Okay. So MPI library is what which enables, in Ubuntu or in Linux system to run a code parallelly with a particular domain decomposition technique. And then after the solution is run, you have to basically reconstruct everything. There is a library defined, which is a function called reconstruct path, which will automatically reconstruct the solution. Yes. Yes, there, as I told, there will be multiple different files as and when you will add more utilities or more complexity. So the one you told, there can be many others, but I told the basic one which is required to solve an incompressible Navier system. The backfill dict, what it does is, if you want to run, for example, an LES simulation, right? So for LES simulations or DES simulation, for turbulence simulation, we want to often initiate the solution from a RANS solution of the same problem. So we first run the simulation with RANS or URANS solvers and let the flow to go to a developed state. And then we take the solution to map to another case folder and basically to initialize another simulation with that result of the fully developed flow of RANS, and then start DES or LES or higher order turbulence simulations for gaining the stability to reduce the effect of the transients. All right, so to do that, we use map field dict, which can map the field variables from one simulation folder to another simulation. Is that clear? Right, so I have explained all these things. Yeah, so coming to the high level programming, there is nothing much to explain. I've already explained. So this is a basic scalar transport equation. Can anybody quickly tell what are the different terms of it? What is the first term is called of this kind of partial differential equation? The temporal term or the unsteady term, right? And the second one, the convective term, then the diffusion term and the gradient of pressure. So this is very similar to our incompressible Navier-Stokes equation. And if we want to solve, if we want to write this high level code in OpenFOAM to solve it, which I will show you in the source code, it basically comes as this. Now, what does this mean? So the function that solves this PDE, the discretized PDE, is called solve. Okay, as easy as that. So you use the function solve. Within that, you write the governing equation in a discretized form. Now, to do that, you have to use multiple, as I said, you have to use first the class of the object-oriented programming and then call the objects and the functions which are defined within the class. Otherwise, if you directly call this function, let's say DDT, OpenFOAM doesn't understand. Where is it located? Where is this code which does DDT located, right? So FVM, which is called finite volume method, is a class defined in the namespace of FOAM, which does implicit calculation. Okay. And the second one is FVC, which is called finite volume calculus. It is another class which is defined within the namespace FOAM, which does explicit calculation. Right? And now I'm not going to define what is explicit, what is implicit. I hope you have all done CFD courses, you understand that. So if we want to actually write the temporal term or the unsteady term, we actually directly describe DDT ddt is the function which does the temporal derivative depending on what type of discretization technique you have defined in the FB schemes. So in the FB schemes, you have defined already, you have told OpenFOAM that when we use ddt function, you do Euler kind of discretization, which is first order accurate, or you can do Frank-Nicolson type of discretization, which is fractional order accurate, etc. Right? Now, because there is rho and u, because here you can see that the rho is implicitly within the ddt operator. That's why it is implicit, and that's why we are using the class FBM. For example, gradient of pressure, we just need grad of. So that's the function which OpenFOAM already understand, and there is no implicit variable within it. So we can directly use FBC. Here. And since, I mean, of course, this equal to this is written. If we take into it in the left hand side, it will be equal to 0. And you don't have to write equal to 0 in this. So if you just don't write anything and make it positive, OpenFOAM will understand that the whole set of equation is equal to 0. Understood? All right. I'm just not going into this contradictory thing, but here is some information on the simulation work. So when you want to do a CFD simulation, a CFD simulation has majorly 3 different stages. One is pre-processing, which involves making the geometry and discretizing the geometry into an appropriate mix. The second stage is solver, which means you solve your governing equation, you discretize your governing equation and solve the governing equation in each of the nodes of that grid that you have generated. And the third or the final one is post-processing. Once you have solved the partial differential equation, in most cases, you will get the state variables or the field variables as the result. And then you can calculate different derived quantities such as forces, gradient of velocity, vorticity, anything you want to, from that basic field variables, which is nothing but pressure and velocity of the solution. So these are some of the tools, and then as I have written here that you can do co-processing or parallel processing in the solution stage if you want to. Now these are some of the tools that normally I use. Is that block mesh, snappy hits mesh? These two are OpenFOAM's inherent meshing tools, where you can actually very easily mesh some simple geometries such as cylinders, flat plates, airfoils, etc. So block mesh does structured meshing, and snappy hex mesh adopts actually a cut cell approach. So you give the geometry and then it cuts the boundaries of the body to give you a mesh. Rest, GMSH and Salome. These two are very powerful open source geometry and mesh processing softwares, which I often use. And of course, if you go for very sophisticated, complex 3D geometries, you can also use the commercial versions of ANSYS meshing or StarCCM, SolidWorks for geometry, etc. Now, the solvers in OpenFOAM are actually categorized into different class of problems, such as incompressible, compressible, heat transfer, combustion, solid mechanics, etc., etc. And then for post-processing, we mostly use Parallel, which is very native to OpenFOAM. However, you can use GNU plot for plotting. You can use Visit for doing some other post-processing calculations. And of course, you can use Snakeplot, which is a commercial licensed version of post-processing unit. You can also do ANSYS itself. In ANSYS itself, you can do. So these are some of the options. Right. So now let's do something on the terminal, and I will, whatever I showed you on the basics, let us see in actual form, right? So I will be showing you all this in the terminal, and You just go back when you have an installed version, just check things whether it works. So before we do anything, okay, on terminal, so this is one very unique thing with OpenFOAM is that it is very much friendly with Linux system because inherently it is evolved as a command line interface tool, okay, which is called CLI, which means that you need to know basic Linux commands to actually go with it because there is no graphical user interface. So how many of you are accustomed with using Linux? Again, 5 out of 30. Okay, so if not, most of you use Windows operating system, I'm guessing, or Mac. Now, Mac also has a unique version of terminal, which actually works almost like Linux, so it's not a problem. But Windows does not have a native Unix version, but it has command prompt. Okay, but the command prompt actually in terminal you can navigate within the operating system. However, it's not very friendly with OpenFOAM software as in general. So what I suggest you to actually, I will now show you the download link and installation instruction before I go into actually doing things in terminal. So in Windows, you have to install something called Windows Subsystem Linux, which now Windows has inherently natively within Windows operating system itself. So you do not have to install Ubuntu separately using a virtual box, which we used to do when we were students. There was no WSL. So now WSL or Windows Subsystem Linux actually has two versions. One is WSL and WSL2, which is the second generation of Windows Subsystem Linux. Once you install that, I mean, there are multiple videos on YouTube how to activate it. I also have a video in my YouTube channel. So once you do that within Windows Subsystem Linux, you have to install a Ubuntu version. So for example, now you can do 2204. Are you aware of different Windows version, right? So you can install the latest Ubuntu version within your WSL, and that is your Ubuntu system. So you can do everything within that, what I will be showing you now. Right, so is that clear? Any queries till this? Okay, can you confirm up to what time this session will go? I'll plan for you. 12:45. Okay. So clear. So let me show you the website and where you can actually download the code. Right. So if you just go to your browser and type openfoam.com, it will take you to the main repository of or main website of OpenCFD where OpenFOAM is hosted. All right. And without, I mean, I don't want to waste time showing you everything here, but just go to download in the openfoam.com and then you go to download and you can see that you have all the different operating system. And if you click one of these, for example, Windows, you will basically go to the current, current stages or instruction. Like for example, this is what I was telling, that you have to install Windows Subsystem Linux, and then either you have to do WSL or WSL2. Then you have to install Linux, which is some version. I would suggest don't go for the open source or something. You can directly install Ubuntu version, which is the recent version. And then you have to install OpenFOAM. And for Ubuntu, here, if you go and click, it will give you the stages on what to do when you have Ubuntu in your WSL. And it's very, very easy because this is already you are compiling, you are copying a pre-compiled version. Initially, what we used to do, that option is also there. If you really like to run or compile codes, you can take the source code and then compile it yourself, which will give you a better idea about what are the libraries that you are installing, etc. But that is a bit involved. So to start with, you can just do this, which is in 2 minutes, you will have this. So it's not a problem. So is the installation clear for majority of Windows users? And for Ubuntu users, it's nothing. It's you just start with this step. So you open your terminal and then start with this step, which involves some of the installing. So when you do this curl base, which means it's actually bringing or downloading the repository or the source file from a repository where it is stored located, and then you are updating your operating system, and then you are installing the OpenFOAM, which is pre-compiled. So it takes very less time. You don't have to really compile all the source code. Sometimes when you do sudo apt-get update, it may not update properly your operating system, and some of the third-party libraries may be still missing. And then when you try to install OpenFOAM, it will show you errors. Right? So this library is not found. So it's as easy as that. You separately install that library and then try it again. So whenever you are actually into programming, I think the most you can learn from your error messages that you get. So do not ignore the error messages or do not get frustrated that I'm getting errors. Just go through the error messages. I mean, the developers have developed it very intelligently, even the error messages, so that they can guide you what is the next step. So if you read the error message, it will clearly tell you what to do next. All right. So till now, I think you know how to install. And then this is the link that I showed you first on the first slide. This is a wiki page of OpenFOAM, OpenCFD version OpenFOAM, where anybody can contribute. Like but it is actually categorized in a very simple way. So the first thing you want to do is first glimpse series. If you go there, it has two simulations, very basic simulation. One is flow in an elbow, another, no, not two, actually 3, 4 now. So it is getting added every year. So lead driven cavity, which I will show you now. Then vortex setting, one vortex setting tutorial, and then one liquid gas interaction multi-phase flow. So basically, this is what you go first. Then when you understand this, you go to the 3-week series, where you have one of my colleagues have like put a lot of effort to categorize it into different weeks so that you can follow it step by step, different aspects. So when you become an intermediate user, you can actually go by these collections of contributors, and if you actually know them, for example, my colleague Joseph Naj is very popular. I think you may have heard his tutorials on YouTube. You might know my colleague Joel Guerrero. He is very very active in contributing and creating tutorials for OpenFOAM. He runs a company called Ulf Dynamics, which gives trainings and which has many free tutorials. So very useful repositories, etc. So that's all. So I just wanted to signpost about these things. Clear? Any questions till now? So people who have laptops with you, which version of OpenFOAM you have? Okay, that's fine. It will work. So you have openfoam.com version. Anybody else? Thanks. You have the foundation version. So mostly it will be the similar syntax. It won't be different, but maybe some things more in, advanced stuff, your syntax will be different. Okay, all right. Let me try to connect to my workstation in my lab in Birmingham so that I can show you something. Hopefully it will be connected. there is a bit of lag because of connecting to the workstation. But just to give you the overview that I've now given them an overall view of different case structures of OpenFOAM, how to install the software and what are the different versions and what we can do with OpenFOAM. Now I'm going to just give them a, hands-on demonstration. The problem is internet is very slow, so it is lagging. Right. In the meantime, in 2-3 minutes, if you have any queries still now, please ask me. The internet is very slow.
Speed is slow there or
If you change the name of the line.
where is the problem? It's internet here or there?
Yeah, because
Yeah,
I'm
slow.
trying to connect to my workstation, so it is the bandwidth is slow. Yeah, can you give me the password again? Sorry, I'm giving. The other option is if you have who has 12.22.06 you have installed, right? So it's Ubuntu or Windows. Do you have Ubuntu or Windows? WSL. Are you joined to the Zoom meeting? Okay, if you can join the Zoom meeting, then probably I can use your laptop. Or the other option is I show you demonstrate you all the things and then I figure out over the lunch and I give you the hands-on in the next session. So that is also a possible solution. Yeah, I think let's go ahead with that. Right, so I will join. So till now, you don't have any queries, right? So you will be able to go to the OpenCFD repository, see the tutorials, and then you will be able to download the source code and install it, depending on whatever operating system you are using. So to get started, as I said, that you need to know some command line interfaces of Linux to easily navigate through different folders of OpenFOAM. Now, the first thing that you want to do before just after installing and before you try to use OpenFOAM is to activate your terminal. So if you are aware of the environment of a terminal, that when you open terminal, whether it is in Windows subsystem, Linux, or in Ubuntu, it will automatically comes with a programming environment or an environment where you basically have to activate or source the basrc file. There is a basrc file in the config folder of the source code of the codes of OpenFOAM. You have to source that file to let your terminal know that my environment is ready for using the different libraries and functions that I want to use for my simulation. Is that clear? And that we do by doing source. Where is your installation directory? That means whenever you are actually downloading and installing or compiling OpenFOAM, you will have a installation directory where you can directly go by the cd command or the call directory command, if you are aware of, to $wm_project_dir, which is your project directory, right? So that would be your path to directory. And then within that, there will be a folder called etc, where all the configuration related files are located. Within that, there is a basrc file. And if you are aware that any operating system you are using, that also has a by default basrc file, which is called system basrc, which even unknowingly you are using some control settings which actually dictate what will be your environment, programming environment, when you switch on your operating system. All right. So this is the same for OpenFOAM. And once you source this, you will be able to see that your OpenFOAM functions are recognizable by the terminal, and it can link all the libraries and the locations of them. So once I get the terminal ready, I will show you all this. Right. So this another thing which you can do, which is advisable, is that without doing this whole command every time, you can just copy this source and the path into your system basrc, so that whenever you switch on your operating system, the OpenFOAM environment is activated and you don't have to do it again and again. Clear? Okay, all right. So, for example, this is also useful, particularly to use different version of OpenFOAM at the same time. For example, as I said, you want to use the OpenFOAM Foundation version, which is OpenFOAM 7, 10, or 11. You want to use the OpenCFD version, which is version 23.12, for example, or you want to use also the Foam Extend version, which I explained before. You could use this alias command to actually create small keywords, which will directly by entering them, you would activate that particular version of OpenFOAM. That's the beauty of it. So you can use 5, 6 different versions of OpenFOAM together, and you just create that keyword. For example, I can create OF7 to activate the OpenFOAM Foundation version 7 by this command, and you can just copy this in your system basrc, so that whenever your system will be on, your environment will be activated. Now, if you give, for example, for me, I use OpenFOAM 2306. This is the keyword to activate the OpenFOAM OpenCFD version. Right. So I would have shown you the etc folder. I will show you later what it looks like, what are the different folders. And then it is very important to know these environmental variables, which would allow you to confidently navigate between different folders of OpenFOAM codes, and to know where your source codes are located and where to go if you want to modify some code, right? So as I said, this FOAM form, here it is written in small, even if it is an acronym. This is the namespace of the object-oriented program environment of OpenFOAM. So when you have sourced this alias or this main basrc file of OpenFOAM, if you type FOAM directly, you would go to the installation directory automatically. So you don't have to really search or type all the path. You just type FOAM, it will take you to the installation directory. Now, this is another thing that I told, that without even typing that, you can directly use the call directory function or the CD to go to WM underscore project directory, not the user directory. If you write on the directory, it will take you the same installation directory. But if you just add the user directory, it should take you to a different folder if you have created, where you should actually run your codes, which should be your run folder. Okay? So within that directory, it is a systematic way of doing the calculation. You don't want to run and generate the simulation data in your installation directory, right? So you have to run the simulation in your user directory. And within this user directory, there will be a run function which can also be taken with this environmental variable, which is $home_run. And if you want to go to tutorial folder, for example, if you go to home tutorials, if you want to go to the source code folders, you go by the src or $home_src. All right. So, right. So this is the folder structure. Again, I think I'll figure out something in the lunch and show you hands-on in my computer. That this WM project directory is the installation directory, as I told. We have these folders. So what are these folders mean and why they are important? This is quite crucial to know, because otherwise it will be almost like again a black box. You don't know where your codes are located, then you can't find where to find the source code and how to modify. So the applications folder is very important because it actually has a subfolder called solvers, where actually all these categorically different partial differential equation solver for incompressible flows, compressible flows, heat transfer, etc., are located, right? Then you have test, which is not very important. There are some test codes to test whether your installation are working properly. Utilities has different utilities such as function objects and other ancillary codes that you may use to process your results, etc. Then this is very important, tutorial folders, where according to the category of the solvers, you have multiple tutorial cases. And as I have explained in the first half, you will go to any tutorial folder and find those primary files that you need to know. And you have to modify to change the boundary condition, to change the solver settings, solution mechanism, etc. All right. Then SRC is the source code folder, where actually all the different digitization source code and all the different source code that you are indirectly using are located. Then you have bin folder. Bin folder, actually you don't have to touch it, but it has all the executables while you compile the OpenFOAM code itself in the name of installation. So there is no specific installation here. You are basically compiling all the different C++ codes, which has different objects and functions for the OpenFOAM code. So all the executable folders are located in the bin folder. Then you have a documentation. Then you have the EDC, which is the configuration folder where the SRC is located. So you have to remember it. Then you have platforms where all the linking temporary, if you know that there are virtual linking between the libraries and the executable files, those files are located depending on your operating system. And you have WMake, which is a important file or important library of the code, which allows you to recompile if you have modified some codes. Clear? Right. So, okay. So if you want to check the path, right? So you just know, for example, you just don't know what is the path of my user directory, whether I have really created the folder or not. For that, you can use this basic command line interface of Linux command called echo. You can give this environmental variable, for example, $WM project user directory, and you can echo it. It will give you the path of the directory on your operating system or on your machine. Where is the path of the user directory? Similarly, if you do the home run, it will give you the path where is your run folder located. Okay. So these are all very basic Linux commands that you can all use even for OpenFOAM. There is no different change in it. Okay. So these I will show you later, not very important. And OpenFOAM alliances, I won't spend much time here, but you can see whatever I've already showed you that SRC means the WM project directory and then the subfolder SRC, lib app solution utility tutorial, all those are basically aliases which OpenFOAM already by default has to link it with the existing folders. Right, and yes, so this is basically again how do you, if you forget something, right? So if you forget the environmental variables, you don't have to remember by heart. You can just use the grep command of the environment of foam underscore. It will give you all the different environmental variables that I just showed you. For example, foam underscore tutorial, foam underscore run, etc., etc. And it will also give you automatically the path of your computer or of your repository. It's a bit old of my computer, some computer where I ran this. It gives me the path of my computer and the corresponding environmental variables. Right. So, any questions till now about the environment? I mean, activating the OpenFOAM environment and how to get the environment variables. So, if not, here basically it's the same thing, but it's also the same thing. So these are part of what I'm planning to show you and so on. So it's important to understand the difference between these two. As I told, one is WM project directory, another is WM project user directory, right? So the WM project directory is the installation directory. So if you try to modify something and compile something within that, it will always show you permission denied error, because it will be located in some part of your operating system where without doing sudo you cannot actually change the configuration settings. So I have seen many people who are just starting, they keep on asking me that why I'm getting error. I mean, they don't even see what is the error. So again, the message is if you are getting some error, that is actually giving you some email. So if you get a permission denied error, which means that you are trying to compile your code in a location where you don't have the administrative permission to do so. Okay. So the idea is whatever you do, you copy the tutorials from WM project directory to the WM project user directory or any other directory of your desktop, download, etc., and then try to run it. Okay, so it is important, very basic but important message. All right, so OpenFOAM case structure I have already explained to you. Just asking again if you have any doubts or queries about OpenFOAM case structure. So you know what are these folders and what are these files, why they are named as 0, constant, etc.
Any problem in OpenFOAM while running any application, we need to use the command say IIT-ISM or something like that. So is that command is connected to the solution file of the system folder?
No, that command is connected to the control D file. So IIT-ISM or PeopleFOAM or PisoFOAM, whatever you are telling, that is the command to call the solver that you are going to use. And that solver is specifically related to what type of simulation you are going to do. Whether you are going to do incompressible simulation or compressible simulation. Whether you are going to do steady simulation or transient simulation. Laminar or turbulent simulation. So based on that, I will show you in the next session. You have to first choose your appropriate solver, and for that again you have to go to your CFD lecture note. That what is the nature of the governing equation and what is the nature of the problem that you are trying to solve, right? So if you want to actually resolve all the scales till the Kolmogorov scales, and you use a RAM solver, you won't get expected results. So you need to understand. So don't take the CFD tools blindly. So the main difference of these open source tools is that it is a bridge between the in-house code where you develop each and every schemes yourself, and the also enables you to connect it towards the main GUI format of commercial codes where you blindly click the box, right? So here you get some flexibility, but you can also get to see the codes which someone has developed. So in the control date, the first line of the control date says you the solver and the solver name. So if you write the solver name, let's say IIT-ISM, but then you call FSI, it will show you error because your code doesn't understand which solver you are calling and what type of problem are you going to solve. Clear? Any other question related to the tutorial? Because when we'll be doing the next things, you need to understand that what are the things that you need to mention to change the boundary condition, solver setup, etc. etc. Okay, so this is where I was answering your question that if you want to use, for example, you need a transient solver for incompressible laminar flow of Newtonian fluids, you can use IIT-ISM. If you want to solve a steady state problem for incompressible turbulent flow, you can use simple flow. If you need a transient solver instead, you can use FSI. Okay, and you have to actually understand the CFD solution mechanism. That what does these solvers do? And you can go to the source code of these solvers and can match with your theoretical knowledge of CFD or mathematical foundation of solution mechanism, such as what is the stability criteria of that particular scheme, right? So simple, for example, it does not account for the unsteady or temporal term of the governing equation. FSI is a transient solver where basically your even people the stability criteria is that your current number or CFL number should be less than 1, less than equal to 1, but it depends also on the implicit or explicit nature of the solution mechanism. Sometimes you can still have more than 1 as CFL number but get a converse solution because your calculation must be implicit in that case. And also again, it relates back to the FD schemes or the discretization schemes and their order of accuracies that you are using. Right, yeah, so in case you use, which we will be discussing in the next session, if you use unit structure interaction or moving mesh problems, you will have to use the dynamic mesh motion strategy. And for that, you need to include that additional dictionary file, which is called dynamic mesh dict. Okay, so this is again, I think, just to show you that if you go to that any tutorial, for example, cavity, you go to the 0 folder, you will have two field variables, velocity and pressure. And within that, you will see something like that first, the dimensions. Everybody understands the difference between units and dimensions, I guess. So these are the dimensions. So any variable or field variable of your governing equation is defined in OpenFOAM as a dimension, scalar, vector, or tensor. Okay? So, for example, here for velocity, you can see L to the power 1, T to the power minus 1. So that is the dimension which makes the code understand that what is this field variable that you are solving for. And then you have the initial condition where in the internal field at t equal to 0, you can define that it should be uniform and in all x, y, z direction the value should be 0 in this case. Then comes the boundary field. Now what are these names? And where did they come from? Moving wall, fixed walls, and front and back. So they are the names that you provide while creating the geometry and the mesh. So in the pre-processing stage, when you create a geometry and either by block mesh or any third-party meshing software and then you import in the OpenFOAM, you have to create the groups of surfaces which would act as either patches or walls. And you have to give them certain names So this problem is for a least different gravity problem, the basic benchmark problem. So we will have one patch at the top, which is actually moving. So we named it as moving wall. We have three faces, which are fixed walls of the cavity. And because we want to solve it as a two-dimensional problem, we have two faces, front and back, where we will actually would not solve in that direction, the governing equation. So that's why we give the boundary condition as empty. So empty is the boundary condition class defined in OpenFOAM. We should tell the code that we do not solve the problem in that discretization direction. And then in the fixed wall, we use no slip. In the moving wall, we use fixed value, uniform 100 means it's one means all units are in SI in OpenFOAM. So we use 1 meter per second velocity in the x direction for the moving wall. All right. And there are different types of boundary conditions depending on the nature of the problem and requirement of the stability of your scheme. You have to use some are fixed values, some are fixed gradient, some are zero gradient. So I think which are very basics as per your CFD knowledge. Right. So I have already explained this, but just to quickly reiterate that in the control dip, you will first have the application, which is, for example, IIT-ISM in this case. Then you will have the starting time, end time, then the delta t value, right control and right interval. So these are important to understand. So these are not time step. This is exactly where you want to write the snapshots containing the field variables such as pressure and velocity for all your domains, all the coordinates or base points. Yeah. So for example, if you want to write the snapshot for each time step, your data will be huge for even if for a simple problem. So, and we don't need that. So depending on the requirement, we can change after how many time steps we want to solve the whole snapshot. However, we can write down the basic field values and forces for each time steps also. So you have the flexibility to change it. You can change your write format, write precisions that, as I told, you can choose how many significant digits up to which you want to write your data to be accurate up to that significant digits. And then you can choose whether you want to use a fixed time step or you want to use an adaptive time stepping based on your maximum current number or maximum CFL. Right. So this is an example of these schemes that you use. For example, you use the time discretization scheme as Euler, which is first order accurate. You can use some higher order accurate method also. You can use different gradient, divergence, Laplacian, interpolation scheme. Okay, so here you have to choose the scheme according to the solution algorithm that you are going to use, and also to the up to the accuracy that you want in your solution. And in every solution, sorry, this heading is wrong. It's not scheme. It's within the solution. It's actually you have to use the solver. Now, can somebody tell what does this solver mean here? What type of solver is this? In the every solution, you are solving some equation, right? So once you have the partial differential equation as your primary governing equation, you discretize using different discretization schemes of different orders of accuracy. And then what is the results that you get? How do you transform the partial differential equation to a set of different equations, right? So what is the nature of those equations? They are a set of linear algebraic equations. So these solvers here means they are linear algebra solvers. Okay. So basically you need to assign some linear algebra solvers such as pre-conjugate gradient method with some preconditional, let's say diagonally incomplete Cholesky. So you know there are different sets of linear algebra solvers and their preconditioning treatment to increase the convergence rate, their stability, etc., etc. And then you can mention the tolerance, the absolute tolerance and the relative tolerance to which these iterative solvers will keep on solving the equation to reach the threshold. And you have to assign those solvers for all the state variables. right? Pressure, velocity, etc. And this is the solution algorithm we show. And you have to mention the corrected loops. And if your maze has high skewness or non-orthogonality, depending on the nature of the maze, for example, you use unstructured meshing, and for some reason it's a three-dimensional maze, so the non-orthogonality of your maze, some locally, some maze elements have high non-orthogonality. You can actually use some non-orthogonal characters also. It can be 0 if you don't need it, it can be 1, 2, or 3, depending on how non-orthogonal your maze is. So those comes under the Pisho control. Right, so I think I'll stop here. And this is a lot of information because I saw that 5 out of 30 participants only have used Open. So I think I don't want to overload you with the information. So before we stop for the lunch, I'm happy to answer any queries.
Sir, although I am using instead of ASCII format, I am using binary format. So is that means I don't know. I haven't checked whether which is the faster in solving solution.
It's not about solving. ASCII or binary is writing.
Right.
So it's data output. When you are getting the solution, you have to write it in a file, right? So what type of file you want to write, whether binary or ASCII, and up to what significant degree. So depending on where you are doing the post processing, it depends on that. Some of the post processing tools prefers to have ASCII files. Some of them prefers to have binary files. So I think ASCII would be a good choice for most of the common problems because normally ASCII files can be converted to different formats as needed. For example, BTK. So if you want to do some post processing with Python and then use ParaView, etc., or convert it to take plot equivalence, BTK files are very important to see the flow field visualization, etc. ASCII can be easily converted to BTK.
No, sir, I would ask that I want to like load my whole solution to the text load, for example.
Yeah.
And if my data is saved in ASCII or in second way, my data is saved in binary. So the loading time, which is taking a lot of the time, is basically it's like 5 minutes, sometimes like 10 minutes. So is there anything which is related to this?
So there is a function, additional functionality called home to BTK. It is a post processing function which will directly convert all your OpenFOAM data into BTK format. So if you are using TechPlot, I think converting it to BTK format first makes sense because TechPlot can easily quickly read BTK file.
So where we can use GNU, we are using binary.
Yeah.
So if we are using binary, we use GNU.
GNU plot, but those are the plot GNU plot. But that is but visualization, yeah, I think BTK format is the most popular format. Yes.
These given solution files, there is a class name dictionary I have seen everywhere, but you don't understand what is the implication of this class.
Where? What is the class?
In the dictionary.
I mean, any of these files are called dictionary, right? So the dictionary file to create a mesh called block mesh dict. The dict means dictionary, right? Creating dynamic meshing is called dynamic mesh dict because it's a dictionary file. So this dictionary class comes from the object registry or the input output method of the object oriented programming of C++. Like when you tell the code to read some data and then based on that write the output, so it will search for a dictionary file where you have already mentioned that this is the way of inputting or outputting, etc., etc. So that's all these control files are called dictionary files.
All these files which are input output type of file comes under the dictionary type.
Dictionary class, yeah, and dictionary class comes and the time class, this comes under the object registry of the total architecture of the code.
Follow the syntax for C++ programming, and you know that C++ is a case sensitive language.
Yes.
Suppose at some point of time, while calling something, I did some mistakes in the using the cases.
So how would I get to know about the errors that is coming related to that?
It will show that the command not found because the code will not understand. So for example, if you use ICO ICO in small fonts, then F capital OAM in font. If you write all small, it will not find the solver. So it will say you like it's a kind of the to test that you can use that banana scheme, right? So if you know that in the while we learn programming, there is a way to find out whether the syntax is correct or not. So it is like that. So because it doesn't follow C++, it is written in C++. So whatever is applicable to C++ is also applicable to this. So it is case sensitive, and you have to give the correct name of the solver or anything that you want. Otherwise, it will say that the solver is not found. So that can be two reasons. One can be you have given a wrong name. The second can be you have not activated the OpenFOAM environment. So in that case, even if you give the correct name, it will not be able to find. So you have to source the bash.rc file. If you forget to do that, it won't recognize that OpenFOAM is installed in your operating system.
That user directory.
Yes, source user directory etc bash.rc. And I told you you can create alias or add it to your system bash.rc so that whenever you switch on your computer or operating system, it automatically activates it.
So it will show us that error at the administrator.
That's a permission denied error. Yes.
But here in this case, it will go on.
It will say that it is not found. This command is not found or this solver is not found. Okay, I'll try to connect to my workstation in the lunch time and I will show you in the terminal. Time is very short, so I plan to talk about the FSI dynamic missing in the next 1 hour, but I'll quickly try to show you in the terminal and then go back to dynamic.
So if I import from here, can I just use the character and orthogonality character and get back the data? Or I have to
Ask me again.
So if I have input some mesh data, can I just use the orthogonality character and get back the data? Or I have to simulate whole simulation, then I will get that.